Here is a number that sounds like a wall, 671 billion. That is the size of one of the most capable open models you can download today. 671 billion numbers, and the gut reaction is obvious. That is for data centers, not for me. I will never run that. But here is the twist this whole episode is built on. The size of a model is not one number. It is secretly two. There is how much memory it takes just to hold the thing, and there is how much work it does to answer you. And modern models pull a trick that pries those two numbers apart, so a model can be enormous to store and yet surprisingly light to run. So the real question was never how big is it. The real question is, which of its two sizes is the one that decides whether you can run it? Let us take the model apart and find out. Before we find the trick, one quick piece of good news. If you opened up a dozen of today's leading open models and looked at their core building block, you would be struck by how similar they have become. After years of wild experiments, the field quietly converged. Almost all of them stack the same kind of layer, the transformer block you already know from Season 1, with the same modern refinements bolted on, a particular way of normalizing the signal, a particular way of encoding position, the grouped query attention we are about to meet, and a particular shape of the little neural network in the middle. There are real exceptions, a few models that do their own thing in one corner or another, and that is healthy. But the headline is, the skeleton is shared. Which is wonderful for us because it means the differences that actually decide whether you can run a model do not hide in 1,000 places. They live in just two. How the model spends its compute and how it stores its memory of the conversation. Everything that matters here comes down to those two organs. Let us look at the first. Here is the first organ and the trick that splits a model's size in two. In a normal model, every single token you feed in passes through the entire network. All of the weights do work every time. A mixture of experts, MOE for short, changes that. Instead of one big middle layer, you build many smaller ones, side by side, and you call each one an expert. Then you add a tiny traffic cop called a router, sometimes called a gate. For each token, the router looks at it and picks just a few experts, maybe 2 out of dozens or 8 out of hundreds, and only those few light up and do the work. The rest sit dark for that token. Watch what this does to our 2 meters. The work done, the compute, only counts the few experts that actually fired, so it stays small and the model answers fast. But the memory meter does not move. Because here is the catch that trips up almost everyone. Every expert, even the one sitting dark, still has to be loaded in memory ready in case the very next token routes to it. So compute scales with the few active experts. Memory scales with all of them. One model, 2 completely different sizes. Now we can diffuse the single most common mistake people make about these models. You will hear someone say, this model has 235 billion parameters, but only about 22 billion are active, so it basically runs like a 22 billion model. Half of that sentence is true, and the dangerous half is false. The true half, it is as fast as a 22 billion model, because that is all the compute that fires per token. That is a real and wonderful gift. But it does not run like a 22 billion model, because to even load it, you still need room for all 235 billion weights, sitting in memory, every expert ready. Active parameters buy you speed. Total parameters set your memory bill. Different currencies and you pay both. In fact, this is so important that model makers now bake both numbers right into the name. When you see a model written as something total with an A and a smaller number, that stands for active. So a name like 100 billion total with 17 active is telling you 2 facts at once. It will answer with the snappiness of the small number, and it will demand the shelf space of the big one. And there is a smaller counting trap worth nailing because it reveals how these models are really wired. Take a famous early one whose name spells out its own math, Mixtral, written 8 times 7 billion. 8 experts, 7 billion each. So it is 56 billion parameters, right? Just multiply it out. Wrong. Its real size is about 46.7 billion. Where did the missing 9 billion go? They were never there. The name makes it sound like you stamped out 8 complete 7 billion models and stood them in a row. But that is not how it is built. Only the expert middle layers, the feed-forward parts, are duplicated 8 times. Everything else, the attention, the embeddings, all the shared plumbing exists exactly once, and every expert borrows the same copy. So you do not pay 8 times over for the shared parts. You pay once. And the lesson underneath the arithmetic is the real prize. An expert is not a whole separate brain. It is just one swappable component inside one shared body, which is exactly why the memory cost is the total of what is actually there, not the sum of imaginary clones. Now the second organ, the one that decides how much conversation you can afford to remember. Back in the inference episode, we met the KV cache, the running memory of everything said so far. For every token in the context, the model stores a key and a value on every layer for every attention head. That cache grows with the conversation, and on a long context it can swell to tens of gigabytes, all on its own. So architects went hunting for a way to shrink it, and they found a beautiful ladder of compromises, each one a name you will see on real spec sheets. The original design, multi-head attention, gives every attention head its own private key and value. Lots of heads, lots of stored pairs, the biggest possible cache. The first idea was brutal multi-query attention. Make all the heads share a single key and value. The cache collapses, but you lose some quality. So the field settled on the sensible middle, grouped query attention. Let heads share keys and values in small groups. Most of the savings, almost none of the loss. That group design, the one written GQA on the model cards, is now the default in nearly every model you have heard of. But one team went further, and it is the cleverest move in the bunch. Instead of sharing the keys and values, what if you compressed them? Before storing anything, squeeze each token's key and value down into a single small summary vector, a latent, and cache only that tiny summary. When you need the full keys and values back, you expand the summary on the fly. You are no longer storing the bulky originals at all, only a compact code for them. This is called multi-head latent attention, written MLA on the spec sheets. And by the lab's own reported figures, it shrank the stored cache by around 93% and let the model serve well over 5 times as many tokens per second compared to their earlier model. Take those exact numbers as the lab's own claim on their own setup. They will shift from model to model, but the direction is what matters, and the direction is dramatic, and it is no longer one lab's secret. Other strong models like Kimi have since adopted the same compress the cache idea. So the same context that once would not fit now fits comfortably, and the same GPU that once served a handful of users now serves a crowd. Same hardware, smaller memory of the conversation. Step back and the whole picture clicks into one clean shape. When you go to run a model, you are really paying 2 separate bills, and the architecture sets both. There is the compute bill, how much work each token costs, and mixture of experts is the lever that lowers it by firing only a few experts at a time. And there is the memory bill, which itself has 2 parts. The weights, the full total, every expert resident, that is your fixed floor, and no clever attention trick removes it. And the KV cache, the growing memory of the conversation, which the attention variants, grouped keys, or compressed latents work hard to shrink. Notice the shape of it. The model maker chose all of this at training time long before you downloaded anything. The number of experts, how many fire, how the cache is built. You inherit those choices completely. You cannot change the architecture. But once you understand it, you can finally read a model's spec sheet and know, before you spend a cent, which bill is going to be the one that bites. So can you run a 671 billion model? Now you know that is not even the right question. The honest answer is, it depends which of its 2 sizes meets your hardware. That model only fires around 37 billion of its weights per token, so in raw compute, It is shockingly light. It would answer faster than you would guess. Its wall was never the work. Its wall is the memory, holding all 671 billion weights resident at once. That is still a serious amount of hardware. But the wall is shorter than it first looked, and it gets shorter still when you compress those weights down to fewer bytes each, which is its own story for another day. And here is what has genuinely changed and keeps changing. Models that a year ago belonged only to data centers are increasingly being run on modest multi-GPU rigs, and even on a single strong machine, precisely because of the tricks in this episode. The architecture is a choice someone else froze at training time and you inherit it whole. But it is no longer a mystery. You can read the spec, split it into its two bills, and answer for yourself before you ever hit download whether this one is for you. That is what it means to actually understand the machine.